Let's have a look at some direction fields and visualize the solution, see what's going on here. This one, as I get at any point, it's actually showing me that slope of the curve. When you have a computer algebra system or some kind of a computer program that draws direction fields, they typically make them all the same length so that you can actually see this on the curve. But as I move along here, this is actually showing me what this would look like. So you can see when I get a larger slope, I have a longer arrow there. You can see how that works. So as I move along here, that's actually showing me the actual correct proportions for that little segment to show you the slope. Now if I click somewhere, it's going to trace out a solution curve for me by following these slopes, and this one's a quite interesting one because our differential equation involves an x to the 2/3 and sine of e to the x, so something kind of interesting. Let's come down here and click for an initial point, and let's see what this one does. And it's tracing out those slopes. So even if we didn't know how to solve this differential equation, we can see what the solution curves look like by looking at the direction field and following those little slopes. So that one's kind of interesting. And here we can see, so the first thing I want you to do is kind of see what your eye sees as you try and follow these slopes, so that you can think of what these curves are doing, and hopefully you can kind of see them. And then let's click on a few so we can watch what it does. And look at that one. Let's try one over here. And let's get one here. Now, why am I seeing what I'm seeing? Now watch as I try and make this point. What is going on right here to the slope? That's going crazy. And if I get over here, whoa, that's going crazy. Why is that doing that? Well, let's look at the differential equation here. dy dx equal x to the 1/3 plus tangent of x. Oh, I see that this is going to be undefined when the cosine equals 0. So what I'm seeing here are vertical asymptotes for these solution curves based on when the cosine is 0. Now that makes sense as I have a look at the differential equation. That helps define what I'm seeing here. Okay, let's look at this one. I want you to look and see if your eye can see any equilibrium solution. And if you see any equilibrium solutions, try and determine from looking at the slope field or the direction field if they are stable or unstable. Now I'm seeing right here an equilibrium solution, but notice I didn't hit it right on. I was a little bit above, obviously, and it took off. Let me try that again. Oh. And you can see the difficulty when you have an unstable equilibrium solution. It's about impossible to be exact on anything. We're going to be off at some decimal place, and so it's going to head out instead of stay stabilized along there. So that's interesting. Our eye can see that equilibrium solution, but I can't seem to hit that. And you can see if I'm a little above or just a little below, that I would head towards infinity or negative infinity. Okay, let's look at another one. Can you see any equilibrium solutions in this slope field or direction field? And I can see one because we're not going to be, maybe they don't have the 0 slopes drawn here, but we're not going to be changing from a positive slope to a negative slope without going through a 0 slope in there. So right along about here, there is a 0 slope. Now I got pretty close to that, but I didn't hit it right on. But what happened now is it is a stable equilibrium solution. Everything is approaching that from below or from above. So even when I tried to hit it and I didn't hit it right on, it stabilized there anyway. So we can see in the slope field, and if we come down here, it may be a little more interesting. And then we come up and then we approach this. This has a typical logistics differential equations curve then as we come up and approach this carrying capacity, or if we start out above, how we decrease until we approach that. Okay, can we see any equilibriums in this direction field, and are they stable or unstable? I can actually see two equilibrium solutions here. I can see one, here's where we have some positive slopes and then we change to negative slopes, so right in here somewhere we have some zero slopes. I missed it a little bit, and what did I end up doing? Heading to another equilibrium solution right here. This one, it looks like I've got it right on here at 0. I can start out down here somewhere and trace out a solution curve, and I approach this equilibrium solution of 0. I can start up above somewhere here, and these guys are going to head out if I'm above this equilibrium solution. If I can hit it right on, I would stay there, but it's impossible to hit it right on, so you can see I end up being either above or below. They head away from this equilibrium solution, but they head towards this equilibrium solution of 0. Okay, what are you seeing for solutions in this direction field? Now we kind of see this interesting thing going on right down along in here. And if I try and kind of hit over in there, let's see what the curves are doing. I'm going to hit a few different ones. And you can see it's kind of like they are radiating or heading out from a specific line. And it turns out right along where I'm trying to hit and can't hit exactly is called a straight line solution. There is a solution that runs along here at a line, but if I'm not exactly on that line, I'm going to either head towards infinity or head towards negative infinity. And this is not an equilibrium solution because we can see this is decreasing as I move along here, but it's following this straight line and things seem to be emanating from that line. So that's kind of an interesting one. So we didn't solve any of these differential equations. We just looked at their direction fields, and you see how much the direction field can tell us about the solution. We can see if it's going to stabilize somewhere. We can see if it's going to go to infinity. We can see if it's going to go to negative infinity. We can actually see the solution without solving the differential equation.